All right, so what is concrete? Concrete is a combination of cement, water, and aggregate. And of course, aggregate can include sand as well as small stones. And reinforced concrete adds steel to that combination and changes its properties in specific ways. So what I'll do is I'll go through the basics of cement and concrete before I talk about how it's used in architecture and construction. Now, reinforced concrete is used for a multitude of structures, including dams, bridges, roads, and even ships. But for today's lecture, I'll be concentrating on buildings. So, concrete is cement-based, which also include mortars. Now, what mortars are is the concrete material that is used to join masonry blocks and bricks. So if you look at this wall over there or that one over there made out of brick, each of those actually are joined with mortar. Okay? And concrete is also used for render, very common in older houses in the ACT in Canberra, which is used basically to plaster over brickwork or stonework to give a smooth finish. Render, because you can control the amount of cement in it, can also be a lot more waterproof than bricks or concrete blocks, but we'll talk about that next week or whenever I give my next lecture, which is about masonry, which is bricks and block and stone. Now, nowadays the cement that we use is called Portland cement. But before that, cement-like substances were made from sand and lime. So they're not as so these kind of sand and lime mortars were not as strong as contemporary cement. Now, lime is not the stuff you squeeze in your beer or in your fish, but it's gotten from the burning of calcium-rich things, which could be things like limestone, but also things like seashells. So this is a very ancient method of, a very ancient way of making old-fashioned cement, which is to burn shells and then to mix it with sand and water to make a kind of weakish sort of mortar, if you like, when compared to modern cements. However, this method, this sand and lime method, was used well into the early 20th century. So I think you could safely say it was used up until the 1930s. As we, as built environment professionals, deal with older buildings in terms of renovations and also adaptive reuses and so on and so forth, this will be important for us, so it's still relevant. One of the things is if you use a modern cement mortar in an old wall that is used where lime and sand mortars were used, and you don't rebuild the whole wall in that, what will happen is that you get one that is much stronger than the other, which will cause you problems moving forward. The other thing is that old bricks aren't as strong as new bricks, and the cement mix may have to be modified to suit. So, concrete is made of cement, you see on the bottom right, water, which I haven't shown, and aggregate. Now, aggregate takes two forms, one being sand on the bottom left and the other being crushed rock on the top right. So if we just look at a minute for concrete's properties, concrete is very dense. We remember that if 1,000 kilograms per meter cubed is the density of water, itself already heavy, we're talking about 2.4 times that. Definitely sinks in water. It's very strong, depending on its composition, right? So the more cement you have in concrete, the stronger it's going to be. These are strengths in compression. It is a bit like stone in that it is a little porous, so it can take it can soak up a little bit of water, depending on the relative humidity as well as the composition of the concrete itself. Concrete is plastic before setting, which means that it comes in a kind of moldable mud, if you like, or a kind of semi-liquid form, which can be poured into a mold, and it will take on the properties of that mold once the mold is removed and the concrete is dry. Concrete is very good in compression, not so good in tension, although it does have some tensile properties. So the main kind of concrete that we use nowadays is reinforced concrete. What reinforced concrete is concrete that is poured over steel bars or steel cables or steel mesh in order to strengthen its tensile properties. So while concrete is no good in compression, it will use the steel's properties to take, while concrete is no good in tension, it will use the properties of steel to make up that shortfall. And then you get, I suppose, almost a perfect material in that it is plastic, can make it into any form, it is good in tension, and it is good in compression. Now, the advantages of concrete are that it is a standardized material with constant properties. It has its strength develops early. After 24 hours, it gets quite a lot of strength with the maximum strength over 28 days. It is easily handled for the construction industry due to its pre-packaged nature in different forms. So you can go to Bunnings and buy yourself a bag of concrete and mix it up yourself, or you can actually buy pre-mixed concrete which already has certain proportions of cement and sand in it. But then you can also get large amounts with batching plants. And batching plants, which I'll talk about in a minute, can be mobile as well. The disadvantages of concrete is that they have a little bit of shrinkage, which may cause a little bit of cracking. Cracking is bad in certain circumstances, not so much for strength, but more for water incursion, which I'll talk about a bit later on. Not everybody likes a lovely grey color of concrete, and the concrete products that come bagged up have limited lifespan, so they tend to solidify by themselves in certain environments, especially environments which have a little humidity. So, moving right along, let's talk about what cement is made of. Cement is made from mixing specific proportions of limestone and clay in a rotary kiln, which is what you see here on the right. And the resultant chemical reaction is a mixture of silicates and aluminates of lime, which is really the things that make cement what it is, or stick to anything else. Now, it comes out in clinker form, which means it's kind of little nuggets of cement, which are then ground into a powder and mixed with gypsum powder, which is that white powder that you use for walls in board form most of the time nowadays, like probably what the ceiling is. And the purpose of the gypsum powder is that without gypsum, the cement would set too quickly. So the gypsum is a retardant. It slows down the setting qualities of it. So this combination is called Portland cement, which is a contemporary form of cement. Now, if we just go and have a look here, what happens is you can see that the rotary kiln, which goes around, right? You can see the big rollers here. So this whole tube actually turns on its axis. In the high end, what you have is you have the feed pipe, which you see in this elevation here, which introduces the limestone and clay, and then it's basically tumbled down this tube, and then they get to a really hot bed, which actually does the work to chemically change the cement, and then it pops out down the bottom here. So you can see that there's a pipe that goes up there which has gas in it, which basically shoots a flamethrower into the tube itself to force this chemical reaction. Now, so once we have cement, then we need to be able to mix it into concrete, because cement powder hardens through another chemical reaction when water is added. Okay, And of course, this is affected by climate and environment. It will take longer to harden in dry and cold climates. It will take longer to harden and dry if the water is not, if it's salt water that you use. It may dry too fast if it's in very hot conditions and so on. But what happens is that basically you can add aggregates like sand and crushed stone to the cement, and the resultant thing that you get will act as a one homogeneous lump, like a big stone. Okay, and this is because the cement reacts with the water and sticks to everything that it's exposed to. The reason why you use aggregates is basically because aggregates are cheaper than cement. So the aggregates are there to pad out the concrete, so you don't have to use too much concrete, because the concrete is the thing that goes through the most processing and costs the most. So what we see here is something that might be familiar to you. On the left is a small domestic cement mixer where you put in your water and your concrete dry mix and turn it on. So basically there's a little electric motor here which turns this thing around, which mixes it. There's a lever there for you to then tip it out into buckets. So this isn't very big, and possibly it's actually used mostly to make mortar for bricks. This one on the right here is a slightly bigger version where you can do bigger lots in the one go. But really these are only for sort of small concrete pours, if you like. When you have larger pours, you need different methods. So by small, I mean, you know, when you're repairing a driveway, or you're casting a few steps, or you're making mortar for bricks and blocks, these are the kinds of things that you will use. Pouring a screed for bathroom floors, and so on and so forth. When you're actually sort of making whole buildings out of concrete, you need altogether different system of doing it. So what we see here on the top left and on the bottom are batching, concrete batching plants. So essentially in each of these big hoppers, over here and over here, we have cement, and we have aggregate, and we might have sand. So we might have different kinds of aggregate and cement and water. And that is basically mixed in specific proportions to give certain strength of concrete, and poured directly into these concrete mixer trucks. So it is actually the concrete mixer trucks that actually do most of the mixing of the actual concrete itself. So this is actually a picture of a mixer truck. But you can see that these things are really quite big things. And in the past it used to be that these things were built in and needed to exist in certain spots outside of towns. But nowadays you can get these kind of mobile ones, which means that you can actually bring the concrete manufacture closer to the site. So what I'll just show you now quickly is, oh, well, it's working there, there you go. So what you can see here is a little GIF of a concrete mixer. So when it goes in, this twisty thing, the drum on the concrete truck actually turns around, and it has this spiral of fins on the outside of it. So when you put it in, it basically, the drum turns around and pushes the concrete into the bottom of it, and hence mixes it up, right? And when which is this, and then the other version is when you turn it around the other way, it tends to pump the concrete out, and then you can use the concrete. Now, what happens is that we know that concrete hardens once water is mixed into it. So there's various ways you can control the rate at which concrete hardens, or really the rate at which concrete sits, or is moved around, and that is done through additives or admixtures. And you can get, I won't go into a great deal of detail here, but just for you to know that these things exist. You can get admixtures which are accelerators, which make the concrete dry faster, and it may be that you want it to get its maximum strength faster, so you put in accelerators. There's retarders, which make it remain liquid for longer. There's air entraining agents, which put little bubbles evenly through the concrete, which is supposed to make the concrete better in situations where there is a freeze-thaw cycle. So in places where it gets down below zero at night and it goes above zero during the day. A bit like Canberra. Although I think it's probably not quite so serious in the context of Canberra. Plasticizers. Now, plasticizers are things that make the concrete mix wetter than what it is, so that it can be pumped around. Pigments, you can put colors into concrete to make it look in a different way that how you want it to. And corrosion inhibitors, which act to stop the steel reinforcing from rusting inside the concrete, and I'll get to that in a minute, or right at the end actually, as to why that is important. So essentially, once you have your concrete truck, it mixes your concrete as it's driving to the site, and once it gets to the site, big pours use these big booms which have a pipe going through it, which are concrete pumps. Okay, so the concrete truck reverses its twist, and actually that is then collected by the concrete pump, which then pumps the concrete to the part of the site where it's needed. Okay, now you can see that this is a very versatile thing. On high-rise buildings, what they do is that they attach the pump to the floors that have already been constructed, and it's pumped up the building still in that way. For small bits, they may actually just crane up a huge bucket of concrete to place in certain places. So, for me, the question would be, how do you know whether the concrete is going to perform in the way that you want it to? What if it's overcooked? What if it starts to harden before it's gotten there, and so on and so forth? How do you test concrete? I suppose is the next question. So the way you test concrete on site is through a slump test. All right. Now that means that you have a standard size cone, which you fill up with the concrete that comes out of the truck. You turn the cone upside down, and then the resultant lump will settle a little bit. And basically, you measure from the top of the cone down to the lump, as this gentleman is doing, and that is known as the slump of the concrete. So for specific strengths of concrete, it needs to slump no more than a certain amount and no less than a certain amount once it gets to the site, right? Which is why they do this on site. On the bottom, you can see that this guy has tipped out his concrete, and the slump is quite it's completely collapsed. Okay, so there may be certain situations where this is necessary, but this is of course a very different kind of slump to what's happening here. Okay, so basically you need different kinds of slumps for different characteristics of concrete. This one may actually be a good thing because they may have put plasticizers in it, and they were testing to see if the plasticizers were still working. Because of course these plasticizers actually stop working after a certain amount of time, so that your concrete can actually set into something hard and not just be a bowl of stone-filled grey mud sitting on the third floor of a building. The other way of testing concrete is compression testing. So what happens here is basically you make these standard solid cylinders of concrete with the stuff that comes in the truck. You let it dry to its maximum strength, which I think is 28 days, and then you try to break it in a hydraulically driven compression machine. Now, you'll all be interested to know that the new workshop that is going in on level A of our building, Building 7, will have one of these machines when the workshop finally opens. So we'll be able to go and crush bits of concrete when the workshop opens. So what happens is that basically the cylinder looks a little like this. You put it inside the machine. The machine applies an amount of force on it, which you can read off this dial here. And basically, once the concrete starts to break, then you know then you read off the amount of force being applied into it, and that's your ultimate strength of the concrete itself. Yeah. And of course, once it breaks, this is kind of what it looks like. Any questions about this? So this kind of testing actually tests the how strong the concrete that you actually poured in your building is going to be. If it turns out that the test reveals that it's not as strong as what it was supposed to be, then you might well have to cut that bit out and do it again. Okay, now we move into the more kind of architectural part of it. Concrete has been used since Roman times, and of course this was the more old-fashioned kind of concrete that was made with lime and sand that I was talking about before. But for some reason it wasn't used much between the Roman times and the 19th century, only for mortar and the like, but not really in terms of mass concrete. But nowadays it's become a very common system and used widely all over the place, all over the globe. So you can see that this floor is probably concrete from the way that it feels under my feet and the way that it's not drummy. And I would suggest that this bit over here is actually not that's still pretty hard. So it's all sort of a concrete floor here, right? So this kind of properties are things that you need to look out for in your day-to-day travels. When you're walking somewhere, just try and see whether you're walking on concrete, because you can't always tell with the coverings that people put over it, right? Okay, so this is an early example of the use of concrete. And I don't mean the walls, because the walls are actually, the walls here are actually made of brick, and these are made of lumps of stone, and there may well have been mortar in between them. But I'm talking about the roof inside this building, the Pantheon in Rome, this version being the 3rd century, because it was built actually much earlier but kept burning down. So this dome with the coffers is actually made of concrete, not reinforced concrete, but just pure concrete. And it's also the weak concrete, which is quite amazing, because it's essentially stood up for nearly 2,000 years. These coffers, or these kind of cutouts in it, are really ways to reduce the weight of the entire thing and reduce the use of concrete. So after this time, not a lot of concrete was used in a kind of massive or homogeneous way like this, until we get to the 19th century, when there began to be a new interest in the possibilities of concrete. Early experiments with reinforced concrete were done by Joseph Louis Lambeau in 1848, who made a ferrocement boat, which is essentially a concrete boat where the reinforcing is steel chicken wire. When I was at uni in my first failed degree of, my first degree that I didn't complete of civil engineering, we actually made one of these things as well, and it was quite amazing that it actually did float. And they still do make the odd concrete boat around the place nowadays. But that's really a kind of a bit of a sideshow in terms of what we're talking about. The first guy to patent a reinforced concrete system was Francois Hennebec, pardon my terrible pronunciation, where he patented basically the kinds of reinforcing that was used, where it was used, and how it was used within the shapes of concrete that were poured around it. Okay, now one of the early modern architects to use Hennebec's system was Auguste Perret, with his 25 Rue Benjamin Franklin apartments in Paris, which employs a reinforced concrete frame. So traditional buildings would have load-bearing walls, whereas these, like you can see here, whereas these walls here are actually all infill. So really, you can kind of get a bit of an idea despite the old-fashioned windows, but it was on the interior that you could really tell, because most of the walls on the interior could actually be placed anywhere on the floor plate, because the columns were actually taking the structure down the building. Now, the more famous use of it was by an architect called Le Corbusier, a French architect who was born in the 19th century and died in 1965. He championed the use of concrete because of its plasticity, because of the way that you could make concrete into any shape. As you can see with his Villa Savoie in Poissy in France of 1931 on the top left. Of course, this is quite interesting because in this case, he achieved these very abstract forms through very old-fashioned construction. So you can see here that he's got a concrete frame with a concrete floor, and then he actually uses bricks or blocks to infill them in order to make this shape. So this is really a bit of an architectural lie, if you like. The abstraction is not achieved through the construction. The abstraction is achieved through old-fashioned means. So this system is really an Anebec system that Perret actually used, and by this stage, a 60-year-old construction tradition. So although Corbusier was really all about the new and the abstract and leaving the old behind, he actually still engaged with old systems in order to get his buildings built. And perhaps this was because either the materials were not available or the technologies had not yet caught up with him. Now, by the time we get to the late 40s, after World War II, Corbusier's work changes. Now, I think it changes because of the technology had finally caught up to Corbusier's ideas about how things should be built. So with this one, which was the Unité de Habitation in Marseille, France, there are a few of these that were built all over France, by the way, which was started in 1848, completed in started in 1948, completed in 1952. We start to see that although there's still a bit of a frame happening, we're starting to have concrete panels that are put inside that frame, and also the legs of the building are starting to be off form or cast in one piece, if you like. Now, this system here is much the same as this system here, and really it's still used in many places of the world, especially in Asia. These were some duplex houses that I did in Malaysia in the 1990s. And what you can see there is that this concrete structure is actually holding up the roof, and these brick walls actually sit inside the concrete frame. They are infill walls which don't have any function in holding the thing up, but it gives you a nice solid feel nonetheless. You can see here how it's made. So you've got the formwork that would be cast into the ground, after which concrete would be poured into it. You can see that this formwork has been used once before because of the grey of the concrete sticking to the insides, and even for sort of beams that are actually bent like this to give you your gable ends, you've got formwork and then you pump the concrete into that. So this is still a very common system. Yeah, it's still a very common system. The other common system that is still now used and also used in Australia is what we would call precast concrete tilt slabs. So this is the way that all of the Cooper Lodge apartment buildings are actually made. So with a concrete frame for which these precast concrete panels have been stuck to. But their origins are actually in things like this. This is Schindler's own house in West Hollywood of 1922, now called the Schindler Museum. Um, and what Schindler did in that case was he was making his own concrete precast panels, and then tilting them up with a block and tackle, as you see over here. So this is also a very versatile material, a versatile method, and it's still being used nowadays. So with the lower rise examples that you might see in your travels around town, up to two, 3, maybe even 4 stories, but I think about 3 stories is the maximum. You can get buildings that are made completely with precast concrete panels without any other kinds of structure. So this kind of technology has developed past the frame. But if you use if you have taller buildings, then you need a frame to hold on to it. Now, going back to Corbusier's Unité de Habitation, you can see basically the use of massive off-form concrete here. So these things, what you see here, are actually the legs here. And you can see the big things of formwork that were made to cast these kinds of things, made with sawn planks, which means that your concrete then gets this pattern of planks onto it. And these things are really a really homogeneous form of concrete where there's nothing infilled here, right? As we talked about before, a lot of this stuff was infilled, but the complete base was cast in situ and off-form. Now, off-form concrete is again very versatile. You have some really amazing efforts at making it do amazing things. So these 2 examples are at the National Sports Complex in Phnom Penh in Cambodia by the architect Van Mollivan, the Cambodian architect Van Mollivan. And he studied under the Beaux-Arts system in Paris at a time where there was no difference between architects and engineers. Okay, so what's amazing about this is that he was the first Cambodian-born architect to go to architecture school, and when he came back, he built this, right? So what they used to teach in architecture school was not only the architectural design, but also the structural design and the constructional design as well. And he was actually the builder or the construction manager on these projects. You can see here the amazing cantilever of this concrete roof, where there's actually ribs in the top of it. And also we can see the ribs here on another stadium. And also you can see this media box where the actual prop that supports the box is actually also where the staircase is. So back in 1964, perhaps you might say that was the heyday of adventurousness in concrete design and construction. They were doing amazing things like this, whereas you don't seem to see it as much nowadays because things tend to be more about money. Some architects, some contemporary architects like Hadao Ando have made a whole career about building, designing houses that use off-form reinforced concrete. RC, of course, is reinforced concrete. So what this is that everything is formed up and poured, and then the formwork is removed, and that remains and that becomes the finished product, or the raw finish, the brute or raw, a brutalist finish, if you like. So moving right along, we might just get into how all this is achieved. So with off-form reinforced concrete, it needs to be cast in situ, which means that what you have is a series of formwork made out of flat panels of things like plywood. This one obviously has yet to be straightened, but once it's straight and you've got your reinforcing inside there, you pour your concrete in it. Make sure all the concrete goes down to the bottom, because otherwise that's going to cause you problems. Not so much from strength, yes, from strength, but mostly from corrosion, which I'll go into later. And then you end up with your kind of monolithic walls like you have there. So this form of construction is mostly used nowadays for retaining walls, as you can see here. So although Ando actually likes to use monolithic concrete, it's actually too expensive in most cases as a construction method, and people save its really high strength for retaining things. So what will happen here is after this is poured and sets, the back will then be waterproofed, and then they will backfill with earth. So this will then become part of the hill back there. Mostly in domestic construction, so in the architecture and building of houses, concrete is used for concrete stumps, for concrete pad footings, when you have timber floors. So concrete is good to sit in the earth because it's very stable in there. As well as, and here we have an example of how the footings are poured. So this is a very efficient way of using concrete because you don't use a lot of it, right? You can see here the concrete stumps that stick out of the ground. Concrete stumps are a Victorian tradition, I think, whereas the ACT tradition is more to use brick piers such as this, so to put two bricks together, crisscross, and up. And then, of course, we can also have steel stumps which sit in concrete pad footings. Of course, concrete footings are also used as strip footings to go underneath the brick walls. And an example of that is here. So this is actually the strip footing that's actually been poured, and it will be backfilled with earth next to it. And then on top of a footing like this, you'll have brick dwarf walls which go around the building. Here you see some brick piers, and on top of this you'll have timber floor structure. As you can see with this image here, it's often quite crude. Dig a trench, whack in some steel, and pour the concrete in. Technically, they're supposed to have a waterproofing membrane that goes over that, but you know, some less formal builders choose to not have that stage altogether. Also, concrete floor slabs are very common in domestic architecture and construction, and from what we can see in this building, this is possibly the same kind of construction here. So what you can see here is a cutaway diagram. So they dig it in, they actually put in a membrane in here, sheet plastic membrane, and then on top of that they put in the steel reinforcing, and then they pour the concrete floor on top of that. Now when you're doing this, you must remember to have all your pipes ready in place, because once you pour the concrete, it's a real pain in the A to get to move the pipes around. So you better be sure that it's not going to cause you grief later. Make trouble for you later. This is a few pictures of that kind of thing, where you've got the prepared site with your plastic and your reinforcing. You see these little things here. They're called, these little hats are really what the reinforcing sits on. So in this picture here, they haven't yet put in those little hats, those little stands. And of course, what you need to do is to get the reinforcing bars off the plastic so that the resultant piece of reinforced concrete will act as a whole, yeah, and so the concrete will move with the steel, and the steel won't pop out of it. Of course, when you're finished, you just see this surface here, which is nice and smooth, and you don't really see any of the beauty of this simple and yet sophisticated construction system. Okay. Now, just to finish up, I'll go through a few of the problems with reinforced concrete. As I said right up the front, concrete can be a little porous and can absorb moisture into it. Now, moisture is the enemy of steel reinforcements because if water gets through the concrete, through the steel will start to rust. Now, the volume of steel rust, or the volume of iron rust, is 7 times the volume of steel or iron. So it's got nowhere to go, and essentially it just pushes out the concrete, and you get concrete spalling, as you see here and here and here. This can also occur if you don't allow your concrete to cure properly, which means that if it dries out too fast, you get shrinkage, and if everything shrinks away from one bit, the bit that it shrinks away from is you're going to end up with cracks, and cracks are also where water can get in. Okay, so this is called concrete cancer, but it is repairable. So to repair it, essentially what you need to do is you need to first of all prop the structure so it doesn't fall on top of you when you start hacking into it. And then once it's propped, then you need to hack into it to cut out all the rusty steel and beyond. And then you need to put in new steel. You need to drill into it, put in new steel to replace the rusty steel, and basically patch it up with a very strong kind of concrete, which will then make it waterproof. If the water is coming from elsewhere, like for example this one, this is a concrete balcony, water may be coming from above, then you may well have to go and re-waterproof the balcony above, or if it's an internal, you may have to go and waterproof the source of water. Typically in older apartments, like 60s apartments which are throughout Canberra, they used to make concrete bases purely out of concrete and without any sort of waterproofing, plastic waterproofing like we use today. And theoretically, the more cement you put into a concrete, the more waterproof it gets. But the problem is that because it's handled by humans in a changeable environment, it's not an ideal sort of laboratory situation, so things do happen, and it happens quite often. The other problem with reinforced concrete would be this efflorescence you get here, which is basically that water gets into the concrete and takes out the salts that have been deposited in the concrete because of the kind of aggregate or water that you used. And you can make concrete with salt water, so this might be the case. And the aggregates that you use to go in concrete, the stones and the sand, need to be washed to get rid of all these kinds of salts. So something like this may also indicate that someone used the wrong kind of sand, wrong kind of aggregate, or that they used the wrong kind of water. Okay, that's it from me. But are there any questions about concrete?